Well, greetings again, machine component designers. Today we're going to talk about one of my favorite topics. Not necessarily technically interesting, but I think it's professionally very interesting. So I'd like to start out with just a couple thoughts about like safety and reliability in our job as engineers, right? And I'll start with a couple quotes. One is a real world recent quote. SpaceX and NASA recently launched their first manned space flight from the Kennedy Space Center a few weeks ago. Many of you probably saw it. And then at the time, the Elon Musk, who's normally this brash, bigger than life kind of guy, was being interviewed by one of the journalists, right? One of the TV people, and this TV personality said, "So what did you say to their families?" Elon Musk had said, "Oh, I just met the families of the two astronauts," and then the reporter said, "Well, what did you say to them?" And Musk was visibly rattled by this, and he kind of took a step back and covered his mouth, to choke back what looked like tears, and he said, and I get goosebumps just thinking about this. He said, I told them we are doing everything we can to bring back your fathers, to bring your fathers back safely, right? I think we're going to do everything we can to bring your fathers back safely. Key words, everything we can. We can't guarantee it. Engineers can't guarantee anything. Scientists can't guarantee anything, right? The best we can do is quantify the risk and say, what is the probability, right? That's the best we can do. On a slightly lighter note, another favorite quote is from Finding Nemo. I don't know if you've ever seen that movie. It's about the little orange fish, and there's like a blue fish and an orange fish, or the orange fish's dad, something like that. And I think the blue fish is named Dory, and Dory is talking to Nemo's dad. I forget his name. But then Nemo's dad is all freaked out. He says, "Yeah, but I promised I'd never let anything hurt him." And then Dory said, "That's a funny thing to promise, right? Because we can't make those guarantees. Things will fail, right? Things will fail." We'll talk about that a little bit. But part of our jobs, and this is a part of our job that we have to take very, very seriously, is to put a price on life, right? We have to say, yeah, every reasonable precaution to make sure this thing is safe, and that's the best we can do, right? If we try to make it a guarantee, the rocket will never get off the ground, the car will never drive, the boat will never float, right? There's always an inherent risk, and we're going to talk about that just a little bit today. Okay. So anyway, let's get into it here. So we're talking about safety factors and reliability. All right. So safety factors in general. Right, this is the wiggle room or the fudge factor, or for good measure, factor included in all designs, right? We know how strong it should be, but we always add in a little extra, right? Or we multiply in a little extra, depending on how we look at it. And if it sounds a little subjective or wishy-washy, it should be wishy-washy. Let's make that wishy-washy. Wishy-washy. It is, right? And so due to this wishy-washiness, you've got to pay close attention to your industry, your company, your country, your culture, because when things get wishy-washy, we have to pay attention to best practices, codes. There's no laws often, there's no law about what size wire to use when you're putting in a ceiling fan, right? But there are codes. They're not laws. You go to civil court, not criminal court. Some places to look. National NSF, it used to be called the National Sanitation Foundation, but they have things that could make you sick are kind of governed by the NSF. CE, Europe has their own thing for being certified safe in Europe. Underwriters Laboratories, kind of the equivalent here in the States. Unified building codes, right? It used to be vary from county to county, state to state, but now across the country, the building codes are all kind of unified. And there's dozens, maybe hundreds more. So if this is overwhelming or scary or not concrete enough to you, welcome to engineering. In engineering, there aren't always right answers. I try to stress that in video number 1. So you'd have to do the best you can, justify the decisions you make, document the decisions you make, document the mistakes you make, right? This is all critical. All right, good. Next slide. Safety factors, selecting the safety factor, right? The first thing is the degree of uncertainty on the loading, right? Now, the example I always like to use are the old piers down at the Union, at Memorial Union, Hooper Sailing Club. Were designed, they're designed and built by some engineering students probably years ago, a bunch of volunteers. They said, well, how many people are going to be on this pier on a busy, beautiful Sunday afternoon in the middle of July? Sure, there could be 20, 30 people on this pier, right? And so they designed this pier such that they designed the pier for 20 or 30 people, right? This is the worst case scenario on a busy Sunday afternoon, right? But what they didn't think about is 4th of July, right? Everybody goes down to the Union to watch the fireworks. And where's the best place to see the fireworks? They've packed 300 people shoulder to shoulder, crammed out onto the pier to see the fireworks. The engineers didn't think of that, right? They thought about what's reasonable. People aren't reasonable. So, and of course, I shouldn't laugh. The pier collapsed, and I think a woman broke her leg. One kid fell in the water, almost drowned because they didn't know how to swim, but yet they're standing on a pier. No PFD. So there's a degree of uncertainty in the loading. All right, the degree of uncertainty in material strength. Fortunately, in today's era, we're better at that. Steel is pretty tightly controlled. The alloying agents and the manufacturing processes are pretty well controlled, but there's still some unknown. If you're dealing with stuff like wood, right? Wood's a natural material. It grows in a forest, right? We don't know exactly how it grew, so there's some uncertainties in material strength. Uncertainties in the relationship between load and stress, right? So which way is the wind going to be blowing on the flagpole, right? That might change. Or how high do they raise the flag? Or what's another example of loading and stress? Oh yeah, we expect the trailer to be driving along on flat ground, but it's possible that if it's on a pitch, right, everything is loaded a little differently at a different angle than the engineer intended. All right. So that might change your uncertainties. Now, how big of a factor of safety do you want, right? Well, it depends on how bad is failure. Let's say I'm building, I don't know, I'm making a slingshot, right, out of some sticks. This is one of those, when I start to do crazy stuff like this and I have weird ideas, I like to show. So I'm making a slingshot, right, for my son or daughter to shoot. And I find a stick with kind of a Y shape, and I find a rubber band. Well, if that breaks, worst that happens, they maybe get smacked in the face, maybe get hit in the eye, like really, really low probability of that. But worst case scenario, it breaks. So I don't really care, safety factor of 1.01, right? Just make it barely strong enough, right? But if it's something like a brake component on a minivan or the brakes on a school bus, the cost of failure is really, really high. Children die, right? And so the cost of failure in life and dollars is important, right? And then further, the cost of providing a large safety factor, right? I could make this safer, but at what cost? So I could make the car a lot safer. I could completely surround the driver with airbags. I could have like a NASCAR style neck restraint. I could make energy absorption, things all around it. So the car is like 30 feet long and 15 feet wide. But then I have to make the highways all bigger, and they're going to use a ton of fuel and blah, 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 blah. So maybe I can't make it as safe as I'd like to, because making it that safe would have all sorts of direct and indirect costs. All right, so safety factors. All right, and now here's another important one, is the definition. Right, now the definition we've done so far is, N is the material strength. So this is kind of the way the engineer looks at it, the engineer approach, right? I say, well, how strong is the material, and what is my expected stress? And hopefully my material strength is greater than my expected stress, so I have something greater than 1. Okay, good. How much greater than 1? I don't know, let's say 40%, right? So 1 point, safety factor of 1.4. Okay, because that's the strength compared to the stress. But there's another important way we have to look at this. and that is the safety factor from a user standpoint, right? What I mean, the load to just cause failure compared to the expected load. What do I, and it's like, well, that's the same thing. Right, let's see if we can come up with an example that's not the same thing. And that is, I don't know what's, as long as we're kind of on an automotive theme today, how about if you have an energy absorption, so here's a brick wall and this is a car. If it's not obviously a brick wall in a car, that's what it is. There goes, you see the lobster boat out there? Yeah, there goes the lobster boat, going out to get some dinner. So here's this car, for that matter, maybe a boat, I don't know. And here's a brick wall. And I impact this, and there's a certain amount of momentum, kinetic energy, whatnot, and then there's going to be certain stresses on the front end of the energy absorption portion of this. Now, of course, we've got his engine pointed right at us. You see him there? Yeah, there he goes. Okay, so it'll get quiet soon. So we know the stresses and we know the strengths, and we can figure out a factor of safety. All right, but think about this. Right, the kinetic energy of this car goes as velocity squared. So if someone says, "Oh, the safety factor is 1.4," so I can really go 40% faster and I'm still fine. No, 40% faster is double the kinetic energy. Right? So is the safety factor 2, or is the safety factor 1.4, or is it 1.02? Right? So we have to be very careful and very explicit with how we define what the safety factor is. Okay, so that's something that most people don't really think about a lot. But there are so the user, they're thinking speed. The engineer is thinking about stress and strength, right? So they're not the same. You have to communicate very well how you're defining the factor of safety. Okay, so now let's get into a little bit here. We've got this safety factor of a diving board. Okay, so we've got the board cross section here. So if I were to draw, let's do this in black maybe. We do this, out here and here. Right, we got the safety, and this is how wide is this thing? 50 centimeters. And then it's 8 centimeters thick here. And then the 100 kilogram engineer stands at the end, right? It's nice that I'm 100 kilograms because I know it makes really good props. So this works out to be 980 newtons. They're standing down there, and then I do a moment balance. So this is pushing up. How much? This is pushing down, but with 980, right? And so everybody should be able to do this by now, and discover that the force at the roller is 3,400 newtons. So this is, whoops, get back there. So F equals 34, I think it's 3432 newtons, right? And then we take the 3432 times this 5 meters, and then we get the moment about the roller equals, what does it work out to be? 4.9 times 10 to the 6th. 4.9 times 10 to the 6th. Wow, that's a huge number. Newton millimeters, right? Newton, let's erase that. Try that again. I'm always terrified to accidentally touch the display the right way. See, and I just did something wrong. Newton millimeters. Why am I doing this in Newton millimeters? Because newtons and millimeters make megapascals, and those are convenient units, right? So, for instance, right here, megapascals. All right, so then I need to know. So we're not going to do crushing. We're going to do crushing a little later in this semester. So we're not going to do crushing. We don't know how to do contact stresses yet. So what's this factor of safety for bending, right? Well, I know the bending stress is MC over I. So it's MC. So sigma equals MC over I. And for this, do I have a blank page here? No. Do I have an MC over I? And the bending stress works out to be, what does it work out to be? 9.194 megapascals. 9.194 megapascals. All right. So that's the bending stress. So sigma bend, right? Okay, so bending stress is that. and I look at this 10 megapascals versus 9.194 megapascals, in the back of my mind I'm thinking, this is not the best diving board. But, right, it's less, right? 9.194 is less than 10, so this thing should be fine. All right. So let's go here. So why did I do this? Safety factor, this slide seems out of order. Stress, velocity, energy, temperature. Yeah, we talked about that. All right. So anyway, back to this. So we discovered that this diving board is in fact safe because I've got, it's only 9 point something for bending and it's 10 for fracture, so we should be fine, right? But there's always a but in engineering. There's always some unknowns. You're engineers, not scientists. Not all engineers are 100 kilograms. In fact, most of you are probably not. I should not be 100 kilograms. I should be less than 100 kilograms. There might be more, right? So the mean, mu is mean. This is the Greek letter mu for mean, which equals average, right? The average engineer is 100 kilograms, but there's some standard deviation of the engine. So this is standard deviation. The standard deviation of an engineer might be 12 kilograms. Okay, and then the fracture strength of the board, sure, the average board is 10 megapascals, right? But there's also some standard deviation to the strength of this board. It might be made out of wood, right? And trees, natural fibers, right, are somewhat unknown. Okay, so we have to consider that, well, there's variability in engineers, and there's variability, or divers, swimmers, recreators, and there's variability in the diving board materials, right? So we have to consider something new called a margin of safety, right? The margin of safety. This is not the diving board, by the way. All right, this is just a random picture out of the book. That maybe I've got some strength that's 70 and I've got some stress that's 40, right? And you might say my safety factor, my factor of safety is 70 divided by 40. It's 1.75. This thing, right, whatever this thing is 1.75 times, it's a factor, times, let's put that in quotes, it's 1.75 times as strong as it needs to be, right? However, there's also something called the margin of safety, like just how much more. It's 70 and 40, so I've got a margin of 30 megapascals. This is dimensionless, and this has dimensions of megapascals, all right? Subtle difference here, but for statistics, we're actually gonna be more interested in the margin of safety. Okay, so the margin of safety is the distance between my, the mean, the mean strength and the mean stress. All right, okay, good, I almost tipped over. I'm standing on really wobbly rocks here, so it's, I just about lost it. So that's called the margin of safety. All right, so let's go back and look at our diving board. Are we ready to look at our diving board yet? Yeah. So I know that, I gotta take my notes off here. It's blowing around in the wind, you can probably hear it. That my strength, so S fracture was 10 megapascal, right? And my sigma bend equals 9.194 megapascals. 9.194 megapascals, right? So that means, there we go. So N, my factor of safety, equals 10 divided by 9.194, which equals 1.088. Right? And that's dimensionless, okay? But my margin of safety, I'm just gonna call that margin of safety equals 10 minus 9.194, and that equals 0.8059 megapascals. Okay, so Yeah, I think that's all we need there. I'll make a note here. So it keeps switching colors. Sorry about that. Redo that. So for here, we need this to be greater than 1. Right? It needs to be at least as strong as it needs to be. And then this just has to be positive. Right? My strength has to be greater than my stress. So the margin of safety just needs to be positive. The factor of safety needs to be greater than 1. All right. Now, a quick little review on the normal distribution. This thing here is the mean. Right? The mean is there. That's the most likely one, the one that happens the most. Well, in this case, the mode and the mean are the same. But that's the average, right? And then the farther out we go, so if I'm 1 standard deviation above, right, that's roughly 34% there, and then 2 standard deviations is another 47%, blah, 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 and this keeps going up. So this picture, right, tells me how likely is something to be, for instance, 3 standard deviations above the mean? Not very much, right? So Olympic athletes, professional athletes, you know, Nobel Prize winners, right? They're all like 3 standard deviations above the rest of us schleps that are just, you know, trying to get by. And then, of course, there's, you know, some things that are way below, right? You know, something that's just bad luck and something failed because it happened to be 3 standard deviations below whatever the mean is, right? But most of us, you know, live right in here, plus or minus a standard deviation in most aspects of our life. 68% of people on all traits are between, you know, plus and minus 1 standard deviation. All right, so hopefully you remember this from stats, but it's a nice little review. Next one. Okay, so now we're going to treat the margin of safety as a normal variable. So now that I'm looking at this, it seems like we could have done a better job. Let's look at this one. Oh, shoot. Okay, so the margin of safety, right, we know that the mean margin of safety, so Z is the margin of safety, is just the mean strength minus the mean stress, right? That makes sense. That the mean margin is the mean strength minus the mean stress. That makes sense. But this is mind-boggling to me here too, that the standard deviation of the factor of safety, or the standard deviation of the margin of safety, right, works out to be the sum of the squares of the standard deviations of the other 2 things. Okay, and I'm going to work through this example, so hopefully this makes more sense, right? So if we look back here, we saw that in this example, the margin of safety was 30, right? I don't know much about the standard deviations here, but then I go forward to here. This is the mean margin of safety. Of course, there could be some margins of safety that are really good, and there could be some margins of safety, that are less than that, right? In fact, what happens when the margin of safety is down here, right? What does that mean? When the margin of safety is down there, oh, that's bad. That is failure, right? It's just bad luck. Bad luck, because here, now, what the heck? You know, this made total sense when I was putting this together. Oh yeah, so this is the case where I just happened to get a weak thing and then a heavy load, and they crossed and it broke, right? So that's what happens when the margin of safety goes red, okay, or when it goes below 0. Okay, so I want to know, my part is, okay, so I want to know if, right, my part is going to break, which is when my stress is greater than my strength, which is when my margin of safety is negative, which is when the margin of safety is less than 0. Okay, so we're not quite ready to go to the tables yet. We still have to work on this a little bit. Okay, so blah, blah, blah. Not all energy units are the same. So I've given some standard deviations here, and I've given this. So let's take a look. My standard deviation, right, and because sigma shows up for stress and standard deviation, my standard deviation for my margin of safety is going to equal the square root of the standard deviation of bending squared plus the standard deviation of the fracture strength squared. Okay. So I need to know the standard deviation of my bending stress. Oh, that's inconvenient. That's a little bit inconvenient because let's see. I know the standard deviation of the mass of an engineer. I don't know the standard deviation of the bending moment, right? But fortunately, the standard deviation or the bending stress, sigma bend, is directly proportional to the mass of the engineer, right? So that means that the standard deviation of the bending stress is directly proportional to the standard deviation of the engineer, right? So then I can write that the standard deviation of the bending stress is going to equal the bending stress itself. The bending stress itself times what is the standard deviation of an engineer compared to the mass of an engineer, right? And if I plug this stuff all in, the standard deviation of the bending stress works out to be 1.103 megapascals. Okay, so 1.103 megapascals is the standard deviation of my bending stress. So now I can take this and I can take that and put it up into here. And what do I do with that? Okay, so now I know the standard deviation of my fracture strength, do I? Yeah, it's 0.8 megapascals down here, right? And now I know I've figured out the standard deviation of the bending moment, so I can plug this stuff in. Oh, what, alert, no, general settings, no, cancel, whatever that is. My standard deviation works out to be, what is this? 1.363. 1.363. And that will be, that's my margin of safety, so that's megapascals. Okay. Oh, so now this is getting to be a little bit interesting, right? So my margin of safety, I figured that out somewhere, is only, my mean margin of safety, where did that go? Is 0.8059, right? But my standard deviation of the margin of safety is 1.363. Okay, so what does that mean? That means this, that my mean standard deviation here is 0.8059. Right? But, right, because that's my mean margin of safety, or my mean Z, okay? But I have to go only one standard deviation below this distance right here. This distance right here is the standard deviation of my margin of safety, which is 1.3. I should have done all this in blue. What does that mean? So it's 0.8059 in the middle, it's 1.3 there, which means that my zero is all this stuff over here is a failure. This is all red. Right, because here's zero. Wow, so a lot of these are gonna fail. How much of these are gonna fail? Right, well, we gotta look that up, so we gotta go to the tables for that. Right, so what this table shows us is what is the shaded area. What is the shaded area, right? That's what this table answers. But it's given in standard deviations. It's given in standard deviations, which I didn't figure out yet. Okay, so I know that my margin of safety is only 0.8059, redo, there we go. So I need my z-score, which equals 0.8059 divided by my standard deviation, which is 1.363, right? So my z-score is only, let's see, where did I write that down? Oh, I didn't write it down. So it's roughly 0.59, I think it was. Are you serious? I think it's equals 0.59. Can't believe I didn't write that down. Okay, so I have only this much room here. 0.59 standard deviations below my average, my mean margin of safety before I get into the negative margins of safety, which means it's going to fail, right? So where is 0.59? Oh, okay, well, it's down here somewhere, right? So maybe on the next page. Oh, sure enough, right? So I'm 0.59, so here's 0.5, and then here's the 0 and 9, so I got to go down here, and I got to go over here, and then I get this. Wow. What does that mean? This is the area of the gray region. So I'm looking at redo 0.28. 28% of my margins of safety are going to be negative. That means 28% will fail. 28% failure, right? That's terrible. Terrible. Now, I'm a practical engineer, but I understand that 28% failure is not good enough. All right, so that's, I'm not going to do this example. So, a little heavy on the math there. Well, not too. There's a lot of statistics. Hopefully that's stuff that you remember from your statistics class that you took like 224 or whatever it is. 324 maybe. But it's critical, right? The math is not hard. Figure out what the mean margin of safety is. Figure out what the standard deviation of the margin of safety is. Figure out how far you can go before it becomes negative, before it becomes zero. Absolutely critical, right? So we've got part of your homework is something about snowboards, right? I one time shattered like full spiral fracture on my tibia. Battery fine. Due to a failed snowboard landing. So it's kind of near and dear to my, well, not near and dear to my heart, near and dear to my leg on this. So I think you're good to go for the homework, and we'll talk to you later.